Intel Rocket Lake is here. It's a new CPU, which means that there's new overclocking features. In today's video, we'll be covering 18 new and improved overclocking features on the Intel Rocket Lake CPU and the ASUS ROG Maximus XIII Apex motherboard. We'll split up the video in 4 different sections.
First, let's quickly go over the Rocket Lake architecture. Then, dig into the new overclocking features and tools introduced by Intel. Then, let's have a look at some of the new overclocking features of the ROG Maximus XIII Apex motherboard. Lastly, let's talk about some overclocking expectations and results.
Alright, we have a lot of ground to cover, so let's jump straight into it. Intel's 11th generation of core products for desktop, codenamed Rocket Lake, was officially announced by Intel during the CES 2021 trade show and officially launched in March 2021.
Rocket Lake is the successor to Intel's 10th generation Comet Lake processors. Rocket Lake sports a brand new CPU core architecture while still on the vastly improved 14nm process node. The CPU core is built upon the Cypress Cove architecture, which is the backported version of Sunny Cove, a core designed for the 10nm Ice Lake processor. Due to the increased core size, the flagship Core i9-11900K offers up to 8 cores and 16 threads compared to its Core i9-10900K predecessor's 10 cores and 20 threads. It does gain support for Deep Learning Boost and AVX512 instructions, a new and improved cache hierarchy, and up to 19% instructions per clock improvement. Other new features include slightly elevated default memory support up to DDR4 3200, 20 PCIe 4.0 lanes from the CPU, double bandwidth of the DMI link, and moving the integrated graphics to the new Xe graphics architecture.
The overclockable K-SKU processors again come in 3 flavors: Core i9, Core i7, and Core i5. Each flavor has 2 variants, a K-SKU and a KF-SKU. The only difference between a K-SKU and a KF-SKU is that the KF-SKU doesn't have integrated graphics. The frequencies of the flagship Core i9-11900K processor are identical to the Core i9-10900K. We'll see a base frequency of 3.5 GHz, an all-core turbo of 4.8 GHz, and a maximum thermal velocity boost frequency of 5.3 GHz. The TDP is 125 watt, and the CPU can boost up to 250 watt temporarily. The frequencies of the Core i7-11700K are slightly lower than the Core i7-10700K. The base frequency is 3.6 GHz, an all-core turbo of 4.6 GHz, and a maximum turbo boost frequency of 5 GHz. The TDP is 125 watt, and the CPU can boost up to 250 watt temporarily. The frequencies of the Core i5-11600K processor are also slightly lower than the Core i5-10600K. The base frequency is 3.9 GHz, it has an all-core turbo of 4.6 GHz and a maximum turbo boost frequency of 4.9 GHz. The TDP is 125 watt, and the CPU can boost up to 180 watt temporarily. Rocket Lake will work on both 500 and 400 series motherboards, though not on the B460 or H410. Obviously, that means Rocket Lake also fits the LGA 1200 socket. Intel Rocket Lake has 14 new and improved overclocking features. Well, some of them are directly related to overclocking, some of them are indirectly related to overclocking, and some are just related to performance tuning in general. We'll go over all of these features and hopefully help you understand a little bit better what they do or how they can impact your overclock. A big change from previous generation Intel CPUs for mainstream is that on Rocket Lake, each CPU has its own individual PLL.
PLL stands for phase lock loop or phase lock loop. Simply put, the PLL generates an output signal, such as a clock frequency. Each core having its own PLL means the processor cores can operate at independent frequencies. The per-core ratio limit allows the BIOS to configure each physical core to its own maximum boost ratio. This enables 2 important new avenues for CPU overclocking. First, it allows users to individually overclock each of the cores and find the maximum stable frequency. Second, it allows users to set an aggressive bi-core usage overclock while constraining the worst cores. This is particularly interesting considering Rocket Lake CPUs have 2 favored cores. Favored cores is part of the Turbo Boost Max 3.0 technology. The favored cores are the cores that Intel deems to be the highest quality among all the cores in your CPU. Not only will these cores benefit from the highest turbo boost ratios available, they will also be prioritized by the operating system when assigning workloads. With per core ratio limit, you can now prioritize one favored core to potentially run one ratio higher than the other core. Note that while each of the CPU cores now has its own PLL and its own VF curve, still only one voltage is applied across all cores. In the ASUS ROG BIOS, you can access the per core ratio limit options via the Extreme Tweaker specific core submenu. In this submenu, you can configure the maximum turbo ratio for each of the cores on your CPU. Note that the favored cores are marked with an asterisk. In my example, I will configure a ratio limit of 53x for core 0, then one ratio less for each successive core, all the way to 46x for core 7. After saving the BIOS settings, I can verify these settings in the operating system using hardware info.
With the inclusion of support for AVX512 instruction sets, Intel has also enabled the option to automatically offset the CPU ratio when such very demanding instructions are detected.
This works exactly like the AVX offset we know from previous platforms. It is just enabled when AVX512 instructions are detected. Both AVX and AVX512 negative ratio offsets are very useful to achieve the maximum performance for both SSD and AVX workloads. Generally speaking, an offset of 2 or 3 is recommended, but it is highly dependent on not only your cooling solution, but also the motherboard you're using. That is because AVX workloads are very demanding and therefore require great cooling and great power delivery. There is a single AVX512 ratio offset that is used for all cores. In the ASUS ROG BIOS, you can access this option in the Extreme Tweaker AVX related controls submenu. As mentioned in the previous segment,
the AVX512 negative ratio offset is a setting that applies to all cores.
However, since the Rocket Lake CPU now supports independent ratios for each CPU core, the AVX offset is referenced against each core individually. This is very different from previous Intel CPUs. Previously, the AVX offset would be referenced against the all-core maximum ratio. So when AVX instructions are detected, the frequency of all cores would be the all-core maximum ratio minus the AVX offset. On Rocket Lake, the AVX offset will be applied to each core separately. That means you have to be a little bit careful when your overclock has different ratios for different cores. In our example, we set the AVX2 and AVX512 offset to 5. Then we also set the per core ratio limit of core 0 to 50, then one ratio lower for each subsequent core, ending with 43x for core 7. In the operating system, we will see that the frequency under non-AVX workloads is 50x for core 0 to 43x for core 7. When we run an AVX workload, the frequency will be offset per core. The resulting frequency is 45x for core 0 to 38x for core 7.
In addition to having an option to reduce the CPU ratio when AVX2 and AVX512 instructions are detected, Intel now has also enabled you to, disable those AVX2 and AVX512 instructions.
Disabling AVX support causes software to take the non-AVX execution paths, resulting in lower performance. It doesn't mean AVX-enabled software won't run, it just means lower performance. To show you the difference in performance, I ran Cinebench R20 with AVX enabled and disabled. With AVX enabled, our score is over 6,000 points. Also notice how CPU-Z mentions the support for AVX, AVX2, and AVX512F instructions. When we disable AVX, our score drops almost 700 points. Also notice how CPU-Z no longer mentions support for AVX, AVX2, and AVX512F instructions. In the ASUS ROG BIOS, you can access this option in the Extreme Tweaker AVX-related controls submenu.
A voltage guard band ensures that the effective voltage stays within the required range to ensure stability.
On Rocket Lake, users are given an option to change the voltage guard band when using AVX2 and AVX512 instructions using the voltage guard band scale factor. The scale factor is a number between 0 and 2, where 0 means no scale factor is applied, and 1 means the default scale factor is applied. The resulting final guardband is as follows. Note that the value of the guardband is arbitrary and may vary from CPU to CPU. Also, it may be a very small value, so adding any scale factor would not show any or very limited results. In the ASUS ROG BIOS, you can access this option in the Extreme Tweaker AVX related controls submenu.
One of the major improvements on Rocket Lake is the memory controller. The memory controller now supports Gear 1 and Gear 2 mode. Gear 1 is the mode as we know it from previous platforms, while Gear 2 is so-called Gear Down mode. In order to better understand how it works, we have to touch a little bit on how memory works.
On DDR4 memory, there are two buses. There's one address and command bus and one data bus. As the name already tells, when the CPU needs to read or write data to the memory, it uses a command and address to specify what needs to be stored and where. The actual data is sent over the data bus. The data bus is DDR, or double data rate, meaning it can send 2 signals per clock cycle. It does this on both the rising and falling edge of the memory clock cycle. The address and command bus is SDR, meaning it can send 1 signal per clock cycle. It does this on the rising edge of the memory clock cycle. As the address command bus is the bridge between the memory controller and the system memory, typically both are synchronized. Gear Down mode is part of the DDR4 specification and allows the address command bus to use every other rising clock, so practically reduce this bus speed by half. This can provide some additional headroom for overclocking at the cost of a performance penalty. In Gear Down mode, the data bus is still using both rising and falling edge of the clock cycle. So, effectively, Gear Down mode is operating at 2T.
Unlike what most enthusiasts would expect, it's not Gear Down mode itself that is the key to those increased memory overclocking capabilities.
As we mentioned, Gear Down mode effectively halves the amount of commands issued by the memory controller. That means the memory controller is now running at twice the frequency compared to the DRAM address command bus. While this is perfectly fine, rather than running the memory controller at twice the speed of the DDR address command bus, on Rocket Lake, Gear Down mode also halves the memory controller frequency.
This is the key to higher memory frequency headroom.
In fact, you'll find that where on previous platforms you had to set very high I/O and system agent voltages for high-speed memory, this is no longer the case on Rocket Lake. In other words, Gear 2 mode enables both higher memory frequency and does so at lower voltages. A definite win-win. Gear 1 mode is supported up to DDR4 3200 officially. From testing, it looks like Gear 1 mode may work all the way up to DDR4 3600. For higher memory frequencies, you'll need to enable Gear 2 mode. However, it's very likely that your motherboard will automatically adjust this when selecting the higher memory ratios. In the table you can see on the screen now, you can compare Gear 1 and Gear 2 mode in detail. In the ASUS BIOS, you can change the gear ratio mode from Gear 1 to Gear 2 in the Extreme Tweaker menu under the item Memory Controller DRAM Frequency Ratio. 1/1 is Gear 1, 1/2 is Gear 2. In our example, we will show the difference in frequency at DDR4 3200. When enabling Gear 1 mode, the DDR4 3200 rated memory operates both the data as well as the address command bus at 1.6 GHz. As the Intel memory controller should be equal to or higher than the address command bus, it is also running at 1.6 GHz. When enabling Gear 2 mode, the DDR4 3200 rated memory operates only the data bus at 1.6 GHz. However, the DRAM address command frequency is halved and runs at 800 MHz. On Rocket Lake, by default, Intel also halves the memory controller frequency to run in sync with the address command bus at 800 MHz. As a consequence of Gear Down mode, Intel has repurposed the registers that were used to enable odd ratio mode on Comet Lake processors. When odd ratio mode is enabled, the memory frequency is increased by an additional 100 or 133 MHz over the resulting frequency, depending on the choice of base frequency. However, The reference clock for memory can still be either 100 MHz or 133 MHz. That means the maximum memory frequency on Rocket Lake is DDR4 6300 with 100 MHz reference clock and DDR4 8400 with 133 MHz reference clock. Of course, you can still further increase the frequency using BCLK overclocking. In the ASUS BIOS, you can change the DRAM ratio in the Extreme Tweaker menu. The setting BCLK frequency over DRAM frequency ratio lets you change between 100 MHz or 133 MHz base frequency. The option DRAM frequency lets you pick a specific DRAM ratio.
While not actually an overclocking feature, ring down bin is very important to keep in mind when trying to get the most performance out of your system.
The CPU ring is the bus that connects all the different parts of the Intel CPU to transfer data between the different cores, between cores and memory, and between cores and other parts of the system. A standard feature of the Rocket Lake CPU and previous generations is that the processor has a power management feature that reduces the ring ratio by several steps compared to the core ratio. In a typical situation, you would see a ring down bin of 3, meaning that if the CPU cores are running at 4.5 GHz, the system would configure the ring ratio to 4.2 GHz. The ring has its own voltage frequency curve, meaning it will request a certain voltage when running a certain frequency. However, the CPU cores and ring share the same voltage plane. So, if you force a specific ring frequency which requires a higher voltage, it is very possible that would result in effectively overvolting the CPU cores. That in turn would increase the temperatures and power consumption. On Rocket Lake, it looks like the voltage requirements for the ring are significantly higher than past generations of CPUs. That means 3 things. 1. At default, the CPU will ring down bin more aggressively to ensure stability with a given core voltage. 2. When overclocking, your maximum ring frequency will likely be constrained by the CPU core voltage you select. 3. When performance tuning, keep the ring frequency for last, as it doesn't have a significant impact on performance, but it does have an impact on temperature and power. In the ASUS BIOS, you can change the ring down bin settings in the Extreme Tweaker menu. By default, ring down bin is enabled. If you want to force a specific ratio, you must disable this option and set a minimum CPU cache ratio. To show you the behavior of the aggressive ring down bin, we ensure the system is running without standard turbo boost parameters. Then we enable the ring down bin option in the BIOS. We can now check the ring frequency in the operating system under a heavy workload. At boot, the ring frequency is 4.2 GHz. Immediately after starting the Prime 95 workload, we see the ring frequency drop to 3.9 GHz. After a while, the ring frequency will further drop to 3.1 GHz and even 3 GHz. This is about 700 MHz lower than the CPU frequency. Every PLL design has a minimum and maximum oscillation frequency called Digitally Controlled Oscillator or DCO frequency. For an all-digital PLL, the DCO operating range is between 1600 MHz and 6000 MHz. In order to generate lower frequencies that are within the minimum range, the PLL's DCO multiplies lower ratios by 2, 4, and 8, and that frequency is divided using a post divider. When the BCLK is increased for overclocking, the logic breaks and may cause PLL banding issues. While this is unlikely to be an issue for daily overclocking, when running the BCLK in excess of 200 MHz, you can set a value lower than 15 to ensure the DCO is within stable range. In the ASUS ROG BIOS, you can access the PVD Ratio Threshold in the Extreme Tweaker Tweaker's Paradise submenu. All the way at the bottom, there's an option called PVD Ratio Threshold.
On previous platforms, the VCCIO voltage was crucial to achieving high memory frequencies. On Rocket Lake, Intel has split the VCCIO into 2 separate voltages, one for the memory controller and one for the rest of the I/O. When overclocking the memory, the VCCIO for the memory controller is the one that needs to increase. A voltage between 1.25 volt and 1.45 volt should be sufficient for memory speeds
up to DDR4 6000 and higher. CPU VCCIO voltage at default of 1.05 volt powers everything else. In the ASUS ROG BIOS, you can access the VCCIO voltages in the Extreme Tweaker menu. In the section with the voltages, you'll find CPU VCCIO voltage and VCCIO MEM OC voltage. It is recommended to set the former option to 1.05 and only increase the VCCIO MEM OC voltage when overclocking the system memory. Another note is that the PCH Z590 chipset is now powered by a VCCIN of 1.8 volts, which is the input voltage for the FIVR. FIVR stands for Fully Integrated Voltage Regulator. FIVR integrates the voltage regulation in the IC to simplify the overall platform power delivery design complexity. Enthusiasts will remember FIVR from the 4th generation Intel Core processors codenamed Haswell. On Haswell, FIVR consolidated 5 different voltage planes, vCore, vGPU, vCCSA, vCCCIO, and PLL into a single voltage input VIN. Extreme overclockers didn't really enjoy the simplified power delivery as FIVR caused the CPUs to suffer from relatively high cold bugs. In the ASUS ROG BIOS, you can access the PCH VCCIN voltage in the Extreme Tweaker menu. In the section with the voltages, you'll find the PCH VCCIN 1.8 volt option. Changing this voltage is unlikely to give you any benefit when overclocking. While delidding a Rocket Lake CPU is not impossible, it can be a little bit tricky due to the solder thermal interface used as well as the placement of the different resistors on the CPU PCB. I would very much discourage users from delidding. However, if you really want to, then you'll likely need specialized tools like the Bauer Delid Die Made or Rocket Delid and Relid Toolkit. I was sent a picture of a delidded Rocket Lake CPU by a good friend. If you were thinking to pop the hood of your CPU just to see what's underneath the heat spreader, I saved you the trouble. Realtime Memory OC allows us to switch between a non-OC and an OC memory configuration at runtime in the operating system. This feature uses the SAGV technology. SAGV stands for System Agent Geyserville. Geyserville is the original codename for the power-saving technology that would eventually be launched as SpeedStep on the Intel Mobile Pentium 3 CPUs. So, it is not a surprise that SAGV dynamically tunes the system agent voltage and clock frequencies depending upon power and performance needs. SAGV itself has been around for several generations of Intel Core processors, but is now used to enable Realtime Memory OC. In the ASUS ROG BIOS, you can enable Realtime Memory OC in the Extreme Tweaker menu. First, make sure to enable XMP. Then, access the DRAM timing control submenu and enable the option called Realtime Memory Overclock. Then save and exit the BIOS. During the reboot, the CPU will train both the standard JEDEC specification and the XMP specification. As it's double the work, this can take up to 2 minutes, so you'll need some patience. After Turbo Boost 2.0 and Turbo Boost Max 3.0, Thermal Velocity Boost is a third layer of Intel's pursuit to give the customer the highest possible performance out of the box. Introduced in 2018, along with the Core i9-8950HK Coffee Lake mobile processor, Thermal Velocity Boost is available on select Core i9 desktop and mobile CPUs. It enables one additional ratio over the Turbo Boost Max 3.0 ratio when the CPU is running below a certain temperature threshold. On Rocket Lake desktop CPUs, that temperature threshold is 70 degrees centigrade. OCTVB or OC Thermal Velocity Boost was introduced along with the Intel Cryo technology not so long ago. OCTVB simply allows the user to manually configure the thermal velocity boost triggers and ratios. We extensively used OCTVB in Scatterbencher 19 and explained the configuration in a video titled Intel Thermal Velocity Boost Explored TVB OC. While OCTVB is included in all Rocket Lake documentation and should be supported at some point, at the moment of recording, the feature has not been enabled yet. That means we'll likely come back to this topic in a future video. When the feature is eventually supported, you'll be able to access the settings in the ASUS ROG BIOS, specifically in the Extreme Tweaker Thermal Velocity Boost submenu. Of course, Rocket Lake still supports a majority of the legacy features that were introduced on previous platforms. Turbo Boost Technology 2.0, BCLK Overclocking, Turbo Boost Max Technology 3.0, TJ Max Offset, Per Core HT Disable, Advanced Voltage Offset or VF Point Offset, the Extreme Tuning Utility, and Extreme Memory Profile or XMP. The ASUS ROG Maximus XIII Apex motherboard has 4 new or improved overclocking features. While some of these features are directly related to overclocking, some are just supporting us to try and get more performance. We'll go over each of the different features and hopefully help you better understand how they work. VLatch is a brand new feature that is available on the Maximus Apex and Maximus Extreme motherboards. It allows enthusiasts to know the true Vmin and Vmax of the CPU V-core without having to purchase a very expensive oscilloscope. Trying to explain how VLatch works exactly can get complicated very quickly, but I'll try to keep it as simple as possible. In one of my previous videos, I talked about Intel Adaptive Voltage Mode. In that video, I showed this drawing to explain how the CPU and motherboard VRM interact to provide a certain voltage. There are 3 basic steps. 1. The motherboard communicates about its board design to the CPU via the AC/DC load line. 2. The CPU requests a certain voltage by using a VID, which is a combination of the factory-defined VF curve and the AC/DC load line. 3. The voltage provided by the motherboard VRM is the requested voltage minus any adjustments by the VRM load line. It's the VRM load line that many enthusiasts wish to have control over when trying to find the maximum stable settings. There are 2 parts of the load line that are important to system stability. First, the V-droop. This is the decrease in voltage when the CPU goes from idle to load. Obviously, you want your CPU to be stable in all scenarios, so knowing what's the lowest voltage the CPU will run at is very important. After all, if the voltage is too low, then the overclock will be unstable. Second, the undershoot and overshoot. These are very brief voltage spikes that occur when the CPU switches from idle to load or from load to idle. These voltage spikes cannot be measured easily and usually require an expensive oscilloscope to detect. I can highly recommend Elmore Lab's article titled VRM Load Line Visualized if you want to see a great picture of undershoot and overshoot in action. While undershoot and overshoot are very temporary spikes, an undershoot that's too low will also cause instability. With VLatch, you can now detect the undershoot and overshoot. On the Maximus XIII Extreme and Maximus XIII Apex, there's a proprietary circuit design that allows the embedded controller to capture and report the true Vmin and Vmax. You can use either hardware info or the OLED display to see these voltages. If you want to use the VLatch feature to figure out which is the best load line for your system, I suggest using the following procedure. First, we must configure the system such that the frequency behavior is dynamic yet controllable. To do this, we unlock the turbo boost power limits of our 11900K CPU, as this will force the CPU to run between 4.8 and 5.3 GHz. We disable AVX2 and AVX512, as this will prevent a high temperature from causing frequency throttling. We disable ring down bin, as this will ensure a consistent CPU ring frequency. We set the max ring to 40x to force the ring frequency at 4 GHz. Then we set the CPU to use adaptive voltage mode. Lastly, we change the VRM load line calibration setting in the DG Plus VRM submenu. In the operating system, we do the following. Open hardware info to lock the information. Start SuperPi32M to run in the background. This will ensure that there's always minimum 1 core active and prevent the VLatch from reporting the minimum voltage when all cores are idle, which would be around 0.6 volts. Run 1 loop of ROG Realbench, which will take about 9 minutes. When done, export the CSV data into Excel and highlight the following information: VLatch min and max and vCore min and max. Then calculate the undershoot as the difference between VLatch min and VCore min, and calculate the overshoot as the difference between VCore max and VLatch max. To find the optimal load line setting, compare the sum of undershoot and overshoot across all load lines. Then, after about 2 hours of testing, pour yourself a glass of whiskey and cry over the fact that, the setting that you figure out should be used is the one that ASUS already recommended in the BIOS. As reported by several media leading up to the general availability of the ROG Maximus XIII series motherboards, Memtest 86 is now fully integrated in the BIOS. Memtest 86 allows the users to test the memory stability without risking corrupting any of the operating system files. In the ASUS ROG BIOS, you can access the integrated Memtest 86 at the very bottom of the Tool menu. Click Activate Memtest 86 to start the test. After the test finishes, it will also store a test report. You can access those in the same menu under Memtest 86 Reports. Since Rocket Lake has a vastly improved memory overclocking capability, I wouldn't be surprised if you see plenty of people running Memtest at DDR4 5866 or even DDR4 6000 using just ambient cooling. I was fortunate enough to be able to try a prototype G.Skill memory kit rated at XMP 5866. Here's the kit running Memtest 86 at XMP speeds with no manual adjustments to either DRAM timings or voltages. The motherboard auto rules set the DRAM voltage to 1.65 volt according to the XMP, sets the VCCIO voltage to 1.448 volts, and the system agent voltage to 1.472 volts. It shows very well the amazing memory overclocking capabilities of Rocket Lake. ASUS Multicore Enhancement is a single BIOS setting that allows you to lift all of the constraints of the Turbo Boost 2.0 algorithm. Effectively, you tell the CPU to run at the highest possible Turbo Boost settings at all times. On Z590, ASUS has enabled MCE by default. For years, hardware reviewers and consumers alike have been very outspoken against motherboard vendors unlocking the Turbo Boost power limits by default. Their key argument is that the CPU is not running at Intel specification. While I understand this argument, I disagree with it. The Turbo Boost 2.0 algorithm consists of 3 key parameters: PL1, PL2, and tau. PL1 determines the long-term power consumption. PL2 determines the peak power consumption, and tau is a parameter used for calculating how long the Turbo Boost can be active. These parameters are chosen to work together with Intel's minimum specification guidelines for motherboard vendors and third-party cooling solution providers. Effectively, Intel promises the customer a guaranteed minimum performance level even if the customer pairs the CPU with a motherboard that has a minimum specification power delivery design and a cooler that has a minimum specification cooling capacity. However, we all know that there are plenty of high-quality motherboards with powerful power delivery designs and solutions like custom loop water cooling that can dissipate well over 300 watts of thermal heat. In this scenario, the customer has purchased the equipment to run the Intel CPU at maximum specification. The maximum specification is determined by Intel's factory set voltage frequency curve, the maximum turbo ratios, and TJ max. In case of the 11900K, a maximum specification CPU will run stably at 5.3 GHz if only the 2 favored cores are active and the package temperature is below the thermal velocity boost threshold of 70 degrees, 5.2 GHz if only the 2 favored cores are active and the package temperature is above the thermal velocity boost threshold of 70 degrees but still below TJ max of 100 degrees, 5.1 GHz if 2 non-favored cores are active and the CPU package temperature is below the TJ max of 100 degrees, 4.9 GHz if all cores are active and the package temperature is below the thermal velocity boost threshold of 70 degrees, 4.8 GHz if all cores are active and the package temperature is above the thermal velocity boost threshold of 70 degrees and below the TJ max of 100 degrees. Therefore, as an enthusiast, I fully approve of motherboard vendors unlocking the power limits by default, especially on products that are targeted at customers who will probably be using high-end liquid cooling. For example,
customers who purchase motherboards with the Z series chipset. Whether I need 125 watt or 350 watt to achieve the maximum performance level is besides the point. It is up to the customer to choose the motherboard and cooling solution that fits their use case. That said, however, I do think it would be smart for motherboard vendors to implement solutions that can ensure system stability in the widest range of scenarios. That's why I also very much approve of ASUS's decision to, by default, enable the package temperature threshold feature. We previously used this feature in Scatterbencher 19. The long story short is that the package temperature threshold will reduce the CPU power consumption if the temperature exceeds a manually defined threshold. The default configuration for the Maximus XIII series motherboards is 90 degrees centigrade. In the ASUS ROG BIOS, you can enable or disable the ASUS multi-core enhancement in the Extreme Tweaker menu. You can configure the package temperature threshold in the Extreme Tweaker AI Features submenu. To demonstrate the behavior at default settings, we leave all BIOS settings untouched. Then we go into the operating system and run a heavy workload like Prime 95 small FFTs with AVX. We use hardware info to track the operating temperature and CPU-Z to check the CPU frequency. We can see that at first the CPU is running all cores at 4.9 GHz. That's because all cores are active and the CPU temperature is below the 70-degree thermal velocity boost threshold. However, almost immediately the temperature increases to over 80 degrees and the frequency is reduced to 4.8 GHz. As the CPU package power hits over 270 watt, the temperature starts increasing slowly. For the purpose of demonstration, we disconnect the radiator fans. This will further increase the operating temperature. Not even 2 minutes later, the CPU hits 90 degrees centigrade. This is the package temperature threshold as configured by ASUS. Moments after the CPU temperature hits 91 degrees centigrade, we see the CPU ratio drop 1 or 2 ratios. ASUS's implementation will very gradually decrease the CPU ratio to target a maximum CPU temperature of 90 degrees centigrade. Almost 3 minutes later, and still running without any fans spinning, the CPU frequency barely drops to 4.5 GHz. Fast forward another 6 minutes, and the system is still running a respectable 4.2 GHz at 90 degrees centigrade. Overall, I think ASUS came up with quite a clever way of providing a maximum possible out-of-the-box performance for their enthusiast customers. The last item on the list is the extended voltage cap options, which you can find in the Extreme Tweaker Auto Voltage Caps submenu. There are options to cap the CPU core, CPU VCCIO, VCCIO Mem OC, and CPU System Agent Voltage. But there's not much more to add than that. In terms of the overclocking expectations, I think we can split it up into ambient cooling and extreme cooling. For ambient cooling, I expect the following maximum stable overclocking results when using high-end liquid cooling. 5.5 GHz for one-core maximum stable frequency, 5.1 GHz for all-core maximum stable frequency, 4.8 GHz for all-core AVX maximum stable frequency, 4.3 GHz for maximum stable ring frequency, DDR4 6133 for maximum stable memory frequency. This is almost the overclock that I managed to get during one of my early recorded test sessions. So compared to Comet Lake, similar single-core frequency range, 100 MHz less for all-core frequency, 200 MHz less for all-core with AVX frequency, 300 to 400 MHz less for the ring frequency, but vastly improved memory frequency capabilities. These overclocking margins are also in line with what we can see for extreme overclocking. To end this video with, I'd like to share with you the Rocket Lake CPU frequency record achieved by the ASUS ROG overclocking team last month. As is tradition now, they used liquid helium to try and squeeze the most out of the new CPU on launch day. The team consisted of Elmore from Elmore Labs and Sam, Shamino, and SafeDisk from the ASUS ROG team. While Elmore focused primarily on obtaining the CPU frequency validation, SafeDisk ran a series of benchmarks with liquid cooling. In the end, they pushed the Core i9 11900K all the way up to 7.3 GHz with the 8 cores enabled. I won't narrate all the footage, but I'll try to annotate some of the video to give you a little bit more insight on how it actually is overclocking with liquid helium. I hope you enjoyed the footage. As per usual, if you have any questions or comments, feel free to drop them in the comment section below, and see you next time.
Okay, 3? Yeah. Okay, let's go for Super Pi 1M.